Our assembly line consisted of 2 workstations. Workstation 1 had 1 operator, and Workstation 2 had 2 operators. This design allowed us to meet the takt time of 24 seconds, however, there was some area for improvement. For example, at Workstation 1, where it was required for the operator to align the spring with the case peg, it was often found that this process created a bottleneck. This was because it was hard to obtain the spring, and it was also hard to align it into the slit of the case peg. Another issue with Workstation 1 was aligning the white piece into the case. This was difficult because the white piece was both small and fragile. Often the operator would have a difficult time aligning it without damaging the white piece. The main issue with Workstation 2 was screwing the case together. This was a problem because the screws were very small and hard to handle. They were also hard to align into the 3 slits. The fact that there were 3 different size screws also meant that the operator took longer to identify which screw to obtain and use. Also, the manual process of screwing in the 3 screws took extra time and reduced productivity. Over a long period of time, this would prove to be an ergonomic risk to the operator's wrists. To summarize, these were the main issues we encountered when developing an assembly line, and this will be the focus of improvement moving forward.
To determine the success of our improvements, we decided the most appropriate metric to use is a difference of means test. Our goal was to complete this test on the main areas of improvement, which includes attaching the spring, inputting the white piece, and the overall screwing process. With these tests, we used a sample size of 30, and to determine whether our improvements were effective, we were looking to see a reduction in idle time in Workstation 2 and an overall improvement in cycle time. Additionally, another metric we used, which stems from Lean Six Sigma methodology, is a value matrix. We use this to identify non-value tasks to eliminate from our overall process. We can determine if the assembly has improved if the time included in unnecessary or non-value added tasks is eliminated. A value matrix is a tool widely used in industry. On the value matrix, tasks are organized to decide required steps moving forward for the task being investigated. If the task falls between necessary and value added, we need to look to improve it. If it falls between unnecessary and value added, we need to investigate further whether or not the task adds value. If it falls between necessary and non-value added, we need to look to reduce the task time. And finally, if it falls between unnecessary and non-value added, we need to eliminate the task.
To improve the step of putting in the white piece, our group brainstormed ideas. Firstly, we labeled this task as a non-value added activity. This is because the tape will effectively work without this part, and it does not add value to functionality from the customer's point of view. Therefore, to reduce this step, our group analyzed the process and identified the majority of this task was spent on unproductive movements, such as adjusting and positioning, to fit the white piece in place. To reduce this, our team colored the end of the white piece as a visual aid. After this iteration, we tested the step with half of the white piece colored. This was the most effective visual aid, eliminating the adjustments and positioning, and therefore the waste. This solution eliminated 3.3 seconds from our cycle time, resulting in a 5.5% improvement and elimination of NBA activities in our process. With the problem of attaching the spring, our team concluded the best solution was to completely eliminate this manual process. However, due to a lack of resources, we further looked for solutions. As a temporary solution, we utilized methodology from the literature, the Toyota Way, 14 management principles from the world's greatest manufacturer. Our strategy was to assign the most skilled worker to this task, therefore effectively managing our resources and workforce. We also standardized the process to only turn the tape once to wind it, reducing non-value added activities, whereas one turn provided enough tension for our spring. Finally, our team brainstormed ideas to improve the flow of materials. Due to our assembly line design, Worker 1 hands the finished part from Subassembly 1, alternating between Workers 2 and 3. This flow of materials is an ineffective use of Worker 1's time and therefore our resources. It also takes precise timing and a level of thought process to produce a staggered assembly line. As well, the movement of materials is categorized as a non-value added activity, whereas it adds no value to our finished product. To eliminate this waste, we prototyped a conveyor belt system. This eliminated the waste in our process, however, had no way of alternating between workers. An alternative solution was including a turntable between the 3 workers. However, due to a lack of resources, this idea was not implemented and we did not use it in our final design.
With the implementation of the electric screwdriver, 21 seconds was eliminated from the total cycle time. This is a reduction of 35%. Not only does this improve the total cycle time, but reduces the long-term fatigue of the operator. This in turn increases the ergonomic value, resulting in a positive impact on the operator over time. Based on the payback calculation, we can tell by the cost of the electric screwdriver and the hour of labor cost, with the 35% cycle time improvement, we would be able to receive the payback in less than 1 hour. The organization of material is important in every manufacturing environment. 5S is a technique used to conduct a high level of workplace simplification. Our team decided to adapt these techniques within our workplace design. All components of the tape measure were separated in different bins based on which workstation they belong to and where they're required in the precedence. This ensures the simplification of the workstations. Another method was the placement of the silicone mat to ensure all parts would stay in place during the assembly. Referencing the 5S methodology again, using the book, The 5 Pillars of the Visual Workstation, we implemented a system that utilized the methodology through the addition of foam screw storage. Each of these 3 different size screws were sorted by color and the section and precedence that they were required, which made it easier for the operator to identify the correct screws and reduce the decision-making time.
As noted earlier, it was decided we would use a difference of means test to determine the effectiveness of our improvements. As our solution to attaching the spring was unable to be tested and implemented, only 2 difference of means tests were completed. The first test was completed on the difference between using a manual screwdriver and an electric screwdriver. A null hypothesis was generated to say the means are the same, signifying no change in task time. This was tested against an alternate hypothesis of the manual mean being larger than the electric screwdriver's mean. Using a sample size of 30 from both sets of data, a sample mean and standard deviation was calculated to use in our t-statistic calculation. With our calculated t-statistic, it was found that we were to reject our null and conclude that there was a significant difference in the means, demonstrating that the task time improved by using an electric screwdriver. The second test completed was on the difference between the marked and plain white piece. In this test, a null hypothesis was generated again to say the means are the same. The alternate hypothesis was that the mean of the plain white piece was larger than the mean of the marked white piece. Using the same procedure again with 2 sample sizes of 30, it was also found that we were to reject our null, which demonstrates an improvement yet again in the task time.
This is a demonstration of our new design of the assembly line. The improvements implemented resulted in a new cycle time of 37.42 seconds, and this reduced our original cycle time by approximately 38%. This reduction allowed us to create 2 workstation assembly line and eliminate one of the workers at workstation 2. This saves us about $20,800 annually. A future recommendation for our design would be to implement a buffer after workstation 1. This was due to the unreliability of the spring and the variability involved in that process. If anything ever occurs to delay production at workstation 1, workstation 2 would be able to pull a product out of the buffer and continue to move tape measures off the line. We were able to do this because workstation 1 was done 1.87 seconds faster than workstation 2. After a certain amount of time, this would allow workstation 1 to add a product to the buffer.
Yesterday we were like, oh, we should put bloopers in the end of our video.
With the elimination of our bottleneck, Laura, we can now meet our jack time. Holy shit, I got a kid.